Hello dear students, I am Praveen, your chemistry educator. Students, in this video, what we are going to do, we are going to cover the full chemical equilibrium chapter. So, in this video, not only all the topics, but I will also tell you the backbone of this chapter. I will tell you a single concept, right, which if you can make it stronger, right, then after that single concept, that one concept, the whole chapter, the whole chemical equilibrium chapter will become very much easy for you. And you know very well that in the NEET examination every year we get at least 1 or 2 questions from this chapter, and that question you can do with ease after watching this video, right? But you need to know one thing, that only learning the concepts will not benefit you. Apart from learning the concepts, you also need to do practice, right? And for your practice, we are providing the DPP in the video description. So from the description of this video, you can download those practice sheet, and those practice sheets you can also get on the PW app. So download PW app, and just like many students, lakhs of students, you can also start your NEET preparation journey. So now students, let's start this session with the very first thing, that what are the topics that we will be covering in this session. So we will start with meaning of equilibrium. So first we will understand what is exact do we mean by the equilibrium state. Then we will talk about what is physical equilibrium, that is equilibrium between your solid state, liquid state, or liquid state, gaseous state, or solid state, gaseous state. Then we will talk about variation of concentration in a reaction, right? Means when a chemical reaction will happen, right? So during that chemical reaction, how the concentrations or amount of your reactant and product will vary, how the concentrations of reactant and product will change, right? Reactant product concentration, how they will change. And then we will see degree of dissociation along with that. And let me tell you one thing, degree of dissociation is a very important point, not only for your chemical equilibrium chapter, but also for your ionic equilibrium chapter, right? Then we will talk about the thing from which we get question most of the time, that is calculation of equilibrium constant Kc and Kp. Kc is in terms of concentration, Kp is in terms of pressure. And followed by that, we will see the relation between Kc and Kp. And from this topic, that is relation between Kc and Kp, we get so many questions in our NEET examination, right? Then we will see properties of equilibrium constant, like what are the features, what are the properties of equilibrium constant we have, and from that also we get question in the examination. Then we will talk about extent of reaction, like how the value of equilibrium constant tells you that how much your reaction has been happening, right? And along with that, we will talk about reaction quotient, QC, right? QC helps you to understand that at any state whether your reaction is going in forward direction or backward direction, right? So extent of reaction, along with that we will talk about reaction quotient, and then we will see a very important relation between Gibbs free energy and equilibrium constant. I hope you know that Gibbs free energy is a parameter we have in thermodynamics, right? So this relation kind of relates 2 chapters, right? This relation will relate 2 chapters, thermodynamics and equilibrium. And we will end this session with factors affecting equilibria, in which you will talk about Chatelier principle and how changing the concentration, pressure, temperature, right, affects the equilibrium state, right? So the very first thing we have to see is the meaning of equilibrium in a process. Students, if you notice carefully, even in your NCERT, right, before chemical equilibrium, you have the chapter thermodynamics. Now, why you have thermodynamics before chemical equilibrium? Because there is a very much valid reason behind it. There is a reason behind that. You know, in thermodynamics, you learn about different processes, right? In thermodynamics, you learn about process like chemical reaction. Then you talk about physical changes. Here I am talking about what we learn in thermodynamics, right? Chemical reaction, physical changes, then temperature change, and then gaseous expansion and compression. Now point is, for any process, I hope you know that there will be a start time. There will be a point when your process will start, and there will be an end time when your process will stop. So point is, for any process, right, when your process gets end, when your process stops, so basically that is an equilibrium state. Equilibrium, if you try to understand what is the exact meaning of equilibrium, right, according to your general life, it's a very simple thing. right? Equilibrium is the state at which a process will stop. Suppose that if I do not talk about these processes from thermodynamics, if I talk about a daily life process, right? Suppose that you are studying right now, right? So studying is a process for you. After certain time, suppose that you stop studying. So when you stop studying, that is your equilibrium state for the studying process. Now for any process, there will be start time, there will be end time, and your when your process stops, so that is called as equilibrium state. Now of course for equilibrium we have different meanings, like we have static equilibrium, we have dynamic equilibrium. Static equilibrium means when your process is not at all happening, and when you say dynamic equilibrium, so that means your process has stopped, but still the process is happening in forward and backward direction with equal rate, right? But overall, in your mind, you need to keep one thing, that equilibrium means stop. Equilibrium means stop. When your process stops, so that state is called as equilibrium. Now, in this chapter, in this chemical equilibrium chapter, what you are going to do, you are not going to discuss the temperature change or gaseous expansion or compression. These two processes you are not going to study in this chapter. Your main focus will be only chemical reaction and physical change. Chemical reactions and physical change. So in a chemical reaction, again, there will be a start time. And when you see that now no change is happening, that means your chemical reaction or physical change has stopped. So when it is stopped, so that is the equilibrium state. That is the equilibrium state. So that's the meaning of equilibrium in a process, right? And if I define this, because in this chapter we have to deal with chemical reaction or physical change. So in this chapter, for the chemical process or physical process, we talk about mainly dynamic equilibrium. We mainly talk about dynamic equilibrium. So dynamic equilibrium, what it says, that equilibrium is the state at which the rate of forward reaction will be equal to rate of backward reaction. Now you can also understand this very easily. If I say that in any reaction, in any process, the rate of forward reaction means the rate from which your reactant is getting converted into product is same as the rate by which your product is getting converted into reactant. So point is this, if the reactant converting to product and product converting to reactant both have same rate, then overall you will observe no change in the amount of reactant or product. So that means what? Overall you can say that now the reaction is not happening, right? Not happening overall. Reaction is happening, but in both forward and backward direction we have equal rate. But overall reaction, it is not happening. So that state will be called as equilibrium. So now I think at least the meaning of equilibrium you have understood very well. The meaning of equilibrium means in a process, in any process, the time when you stop seeing change, the time when your process stops, so that point is called as equilibrium. Now after understanding what is the exact meaning of equilibrium, now let's first see, right, equilibrium in physical states. You know very well from your 9th, 10th class onwards that what is the meaning of solid state, liquid state or gaseous state. Point is, when you convert a solid into liquid, that is melting. When you convert liquid to gas, that is vaporization, right? When you convert solid to gas, that is called sublimation. So these are physical changes, and during these changes also we can establish equilibrium. So first let's take an example of conversion of solid into liquid, and let's understand what is the meaning of equilibrium in this conversion. So point is, let's understand this in a very simple way. Point is, suppose that I took a closed container, So you need to remember one thing, that equilibrium can be established only in a closed container, in a closed container, closed system. Again, that was the point in thermodynamics we had. So I have taken a closed container, and now suppose that here I have a matter in solid state. I have a matter in solid state. I have a matter in solid state. Now, to convert into liquid state, what I will do, I will supply energy, right? I will supply heat energy. So when you will heat it, right, and a certain temperature has been achieved, right, that temperature you can say melting point. When your temperature is equals to your melting point. So at melting point, what happens? The solid will start converting into liquid, right? Now you will have liquids also, which will form slowly, bit by bit, molecule by molecule, atom by atom, right? So slowly, some of the solids has been converted into liquid phase, right, at melting point. But you will notice that after certain time, this melting process will stop. If your temperature is constant, that is, it is equals to melting point. And when it will stop, right, you will notice that in your container you have some liquid, and again you have some solid. And here the solid and liquid, they are said to be in equilibrium state. They are said to be in equilibrium state. So point is, for the melting process, right, at melting point you get an equilibrium state between the solid phase and liquid phase. Or in other words, in physical terms, you can say like this, that when equilibrium is established in melting process, so you have a mixture of solid and liquid in your container. Similarly, you can talk about other conversions, right? Suppose that I have a liquid and I am converting it into vapor phase. I am converting that liquid into vapor phase, that is vaporization. Again, I will take a closed container. I will take a closed container. Initially in this container, I will have only liquid. I will have only liquid. I will heat it. I will heat it at certain temperature, and in this case, the temperature will be equals to the boiling point of the liquid, right? Now, when your temperature is equals to boiling point, right, some of the liquid will vaporize, and your particles now, it will be in vapor phase. So, during the process, when your process is going on, so during the process, what will happen, right? One by one, the particles from liquid state, it will go into vapor state. So during that time your process is happening. But here again, after certain time, you will notice that the conversion of liquid into vapor is stopping, right? And when it will stop, you will have a fixed amount of vapor. You will have a fixed amount of vapor in your container, and you will have a fixed amount of liquid in your container, right? And at your boiling point, in the closed container, you will have both liquid phase and vapor phase. So here we have established a equilibrium between liquid phase and vapor phase. And similar concept you can apply for the sublimation. Now, point is, if I apply here dynamic equilibrium, so according to dynamic equilibrium, after certain time in the conversion of solid to liquid, why we are getting equilibrium state? Why overall we don't see any change? Because the rate of forward is equals to rate of backward. And here you can see like this, that when solid converts to liquid, that you can say melting. So rate of melting will be equals to rate of freezing, right? That's why you have equilibrium state in that physical process. In this case also, after certain time at boiling point, right, if you have a equilibrium between liquid and vapor, now that means no overall change is happening. So the dynamic equilibrium concept here, if I apply, I can say that rate of conversion of liquid to vapor, you can say vaporization, is equals to rate of, when you convert vapor into liquid, that you can say condensation, right? So rate of vaporization is equals to rate of condensation, right? So that is the concept of dynamic equilibrium in your physical changes, right? But of course, you people know very well that in this chapter, most of the time you have to talk about chemical reactions, chemical changes, right? Sometimes you get questions from the physical change or physical conversion of solid into liquid into gas, right? Now, let's talk about a point, that is reversible or irreversible reaction. In thermodynamics, you must have seen this reversible and irreversible reaction. Point is, when it is a reversible reaction, you can also say that reversible reactions are those reactions which are almost incomplete, and irreversible reactions are those reactions which are complete. So here what we are saying that the chemical reactions we have, we can classify that into two parts, right? Some of the chemical reactions are there which are complete, and some of the chemical reactions are there which are incomplete. Now let's try to understand this with an example, although it's a very easy point, but let's understand this with an example, right? Let's understand complete and incomplete reaction. Students, suppose that I am doing a reaction in which a reactant A is converting into twice of B plus thrice of C. So this is my equation for the reaction. Now point is, at certain time I will start the reaction, right? So when I start this reaction, it is called initial state of the reaction. And if you see that according to the time, if you take time as your reference, so initial state is also called as t equals to 0 second or 0 minute, whatever time unit you use. Now initially, by default, we assume that we do not have any product. We do not have any product in the container. Sometimes you can have a product in your container already present, but most of the time by default we assume that in our container we do not have any product. Initially we have only reactant. Now in this case I am saying that initially I have 10 moles of A. Initially I have 10 moles of A. Now when the reaction will start, A will start converting into B. The process will go on. The process will go on and on, right? Now what I observe that at the end, right, or when this reaction is stopping, right, I am having 0 moles of A. What is the meaning of this? I took 10 moles of A and now I have 0 moles of A. That means what? Whatever A I kept in the container for the reaction, right, the whole amount now has been converted into product. So if the whole amount of reactant is reacting and it is converting into the product, so that is called complete reaction. That is called complete reaction. When the total amount of reactant you have taken, right, it is reacting. So the reactant will become 0, or when you have more than one reactant, then you can say that limiting reagent, right? The limiting reagent will become 0. So in this case I have only one reactant, so it has become 0. And again you can apply stoichiometry. You can say like this, that 1 mole of A can produce 2 mole of B, 3 mole of C. So 10 mole of A, if it is reacting, it can give you 20 moles of B and 30 moles of C. So this type of reaction in which the reactant is completely reacting and it is becoming 0, or the limiting reagent is completely reacting and it is becoming 0. So these types of reactions are called as complete reaction. This is called complete reaction. And you are not going to observe equilibrium in these types of reaction in between the initial and end state, right? The reaction will start and it will stop only when the limiting reagent becomes 0, right? And that's why in this chapter we are not going to focus much on the complete reaction. Our major focus is, in this case, incomplete reaction. I hope that by understanding complete reaction, now you have already understood, or you must have guessed, what is the meaning of incomplete reaction, right? Incomplete reaction is a type of reaction in which, right, the reactant or the limiting reagent will not react completely. Some of the amount of your reactant will react and some of the amount of reactant will remain unreacted. So when certain reactant is remaining unreacted, when the limiting reagent is remaining unreacted, so that type of reaction is called as incomplete reaction. Now let me tell you this again with an example. Suppose I have this reaction, PCl5 converting to PCl3 and Cl2. Now here again, for this reaction, for this process, I will have the initial state, right, or t equals to 0. Here again I can assume that initially I had only reactant. So let's say that I had 10 moles of PCl5 again, and by default I am taking product as 0. Now point is, when this reaction will start, so initially when the process will go on, again your reactant will convert into product, right? But we have taken 10 moles of PCl5, right? The whole 10 moles of PCl5 will not react here, right? In this case, what you will notice that after certain time, it has become from 10 mole to 6 mole, right? So when it became 6 mole from 10 mole, so total 4 mole of this PCl5 is reacting. I hope this is a very easy thing. You can easily calculate that, right? That initially it was 10 mole and after certain time now PCl5 is 6 mole. So that means 10 minus 6, 4 moles of PCl5 has reacted. Now if 4 moles of PCl5 is reacting, right? So again apply stoichiometry. 1 mole of PCl5 can give 1 mole of PCl3, 1 mole of Cl2. So 4 mole of PCl5, if it will react, it will give you 4 moles of PCl3 and again 4 moles of Cl2. Now point is, after this state, right, we are observing no change. Now we are not having change in the amount of PCl5 or PCl3 or Cl2. Point is, think like this. If now the amount of reactant product is not changing, what is the meaning of this thing? That now overall reactant is not converting into product, or neither your product is converting into reactant. So here we have established the dynamic equilibrium. This is your equilibrium state, students. When you see no change further in the amounts of reactant product, so that's because now the rate of forward and backward is equal. So this is called your equilibrium state. And these types of reaction where the reactant or the limiting reagent remains unreacted, some of the amount remains unreacted, so this type of reaction is called incomplete reaction, right? And if you notice, so in this case, if this is your initial state and you hypothetically assume that when it will become 0, so that is your end point. So equilibrium is lying in between your initial and end point, right? And that's why these reactions are called incomplete reaction. These are called incomplete reaction. So in our chapter, we will be focusing more on this part, that means incomplete reaction. One more point, I should tell you one thing, that's very important. You know what? In chemical equilibrium, stoichiometry is a backbone, students. Stoichiometry is your first chapter from class 11th, right? And stoichiometry is a topic in which you calculate how much product you are getting from reaction of certain amount of reactant, or vice versa. If you know how much product you are getting, so from that you can calculate how much reactant is reacting. So that calculation, that stoichiometry is like a backbone for this chemical equilibrium chapter. Not only in chemical equilibrium, even for your ionic equilibrium chapter, right? Stoichiometry is backbone. So if you are weak in stoichiometry, please read that first. Please make that topic stronger and then come back to this chemical equilibrium, right? You can find the one shot of first chapter, right, at the PW NEET English channel, and you can learn stoichiometry from there. And after completing stoichiometry, right, you can understand this chapter in a very easy way, because again I am telling, stoichiometry is backbone in this chapter. But if your stoichiometry is good enough, of course you can understand chemical equilibrium with me in a very easy manner, right? So now, after understanding what is a complete and incomplete reaction, and after understanding that in this chapter, we have to focus more on the incomplete reactions in which in between we get equilibrium state. Now let's talk about, right, certain graph that we have to discuss about concentration of reactants and products, right, in a chemical reaction. See, it's a very general thing. You take any chemical reaction, any, whether it is complete or incomplete. So from the initial state, when you have certain amount of reactant and when your product is 0. Let me take an example here. Suppose I take this reaction, N2 plus 3H2 gives 2NH3. And you notice that reversible or incomplete reactions, they are shown by double arrow, right, forward and backward arrow. And if you talk about irreversible or complete reaction, so they are shown by single arrow, only in forward direction. If we have a reversible or incomplete reaction, right, it's a very famous, it is called Gibbs process. and assume that initially when I started this reaction, so initially I had certain like 20 moles of N2 and 20 moles of H2, and product was 0. So from this point, when your product is 0, right, and you have certain amount of reactant for any reaction, right, what will happen? When your reaction will proceed, the reactant will convert into product. So with time, the amount or concentration of reactant will decrease and the amount and concentration of product will increase. This is a generalized thing and it will happen every time for any reaction, even it is complete or incomplete, right? If you have certain amount of reactant and your product is 0, so from this state, your reaction will always go right in forward direction, and with time amount of reactant will decrease and amount of product will increase. Now the same thing, if I want, I can explain graphically. Like suppose if I draw a graph here, if I draw a graph, right, between amount or concentration on the y-axis, and you can say time on the x-axis. So from the initial stage, from the initial phase, right, the amount of reactant which was initially 20 mole for N2, it will decrease, right? Even the amount of H2, right, which is 20 mole initially, it will also decrease, right? And the amount of product ammonia, right, it should increase. So during the course of reaction, the time till when your reaction is happening, continuously amount of reactant will decrease and amount of product will increase. This is a general point. Now, once you achieve equilibrium state, right, once equilibrium has been established, right, then there should be no change, no overall reaction should happen. So after achieving equilibrium, let's say that at this time we are having our equilibrium state. So once you reach equilibrium, right, the amount of product, whatever it is at equilibrium, it will remain constant, right? Similarly, whatever amount of reactant you have at equilibrium for N2 or H2, right, it will now remain constant. So we can say like this, by looking at the graph of amount versus time for reactant and product, that once you achieve equilibrium state, after that state, the amount of reactant and product remains constant. Why it remains constant? Because no overall reaction is happening. One more thing, like this is the example for N2 plus H2 gives twice of NH3, right? Now the graph can vary. Depending on the reaction, right? Sometimes the graph can be like this. Sometimes the graph can be like this. This is the variation of reactant. This is the variation of product, right? And after equilibrium, both reactant product are constant, right? So the graph can look like this, crossing, like amount of reactant and products graph, they are crossing each other. Sometimes it can look like this. They are not meeting each other, but after equilibrium, again, amount will be constant, right? And sometimes it can be like this. All possible things are happening, possible. Yeah, they can meet. So these graphs, right, it depends on what reaction you are performing, right? For different reactions, it can be different. But one thing is common in each graph, that with time, amount of reactant is decreasing and amount of product is increasing, right? In the first graph, if you notice, when we established equilibrium, right, so amount of product is more as compared to reactant. So in the first graph at equilibrium, the amount or concentration of product is more as compared to amount of reactant. In the second graph, this is my reactant, this is my product. If you notice, so in the second graph, when we established equilibrium, so in this case, amount of reactant or concentration of reactant is more as compared to product, right? And in the third graph, if you notice, the concentration or amount of reactant or product is equal at equilibrium. So all possibilities can happen, right? Your reactant can be more at equilibrium, your product can be more at equilibrium, both product and reactants can be equal at equilibrium, right? These are three possibilities we can have. But one thing is common every time, that amount of reactant or concentration of reactant will decrease and amount or concentration of product will increase as your reaction proceeds from initial state to the equilibrium state, right? When you have certain amount of reactant initially and when the product is zero initially. So now I think you have understood very well that how amount of reactant products changes during the course of reaction and what happens at equilibrium, right? Now with this point, now let's talk about degree of dissociation. See, degree of dissociation, it is denoted by alpha. And it will be useful for you in the both chemical as well as ionic equilibrium chapter. So for every students, my first suggestion here is, do not complicate degree of dissociation. Think like this, that degree of dissociation is a information for you. It's an information, students. Degree of dissociation is an information for you. It will tell you that from initial state in any reaction, when you reach equilibrium, so from initial state till equilibrium, how much reactant is reacting. So from initial state to equilibrium, how much reactant is reacting, that information you get from degree of dissociation. Because it is defined as, degree of dissociation is defined as amount or concentration reacted till equilibrium divided by initial amount or initial concentration taken. Initial amount taken, right? So from this definition itself, you can notice that if I do multiplication, cross multiplication, so I can say that amount reacted till equilibrium for the reactant is equals to initial amount taken multiplied by alpha. So how much amount of reactant is reacting till equilibrium, you can directly get just by knowing what initial amount of reactant you have taken, right? And what is your degree of dissociation. Let me explain this with an example again. Suppose I have a reaction like this, in which calcium carbonate, it is dissociating into calcium oxide and carbon dioxide. I hope you know the phases. Calcium carbonate is solid, calcium oxide is solid, and carbon dioxide is a gas. Now point is, initially we are given 5 moles of calcium carbonate. Initially they are saying that we started the reaction with 5 moles of calcium carbonate, and the initial amount of product by default it is 0. Now in the question, if they mention that the degree of dissociation of calcium carbonate, is 0.2. If it is given that degree of dissociation of calcium carbonate is 0.2, so we can calculate till equilibrium how much calcium carbonate will react, right? Because alpha, degree of dissociation, is amount reacted upon total amount taken, right? So here again alpha will be reacted amount upon initial amount, which is 5. So reacted amount here, it will be 5 into alpha, 5 into 0.2, which will be 5 into 0.2, I think it is 1 mole, right? So initial amount into alpha gives you how much amount will react till equilibrium. So in this case 5 into 0.2, that means 1 mole will react till equilibrium, and from this we can calculate amount at equilibrium. Now I can easily find out that when I will reach equilibrium state, so initially it was 5 mole, 1 mole will react till equilibrium. So 5 minus 1, at equilibrium the calcium carbonate will be 4 mole. And again, by applying stoichiometry, I can find out the amounts of calcium oxide and CO2, right? Because 1 mole of calcium carbonate is reacting. So according to stoichiometry, 1 part can give you 1 part of calcium oxide, 1 part of carbon dioxide. So 1 mole of calcium carbonate, if it is reacting, it will give you 1 mole of calcium oxide and 1 mole of carbon dioxide. So this is what I am saying, that always treat degree of dissociation as an information, right? Because it will help you to calculate how much amount of reactant will react till equilibrium. And if you know how much amount of reactant is reacting till equilibrium, you can find out, right, the equilibrium amount or equilibrium concentration. And believe me, I said earlier that stoichiometry is the backbone for this chapter, right? And why I said that? Because using stoichiometry only, students, you can find out the equilibrium concentrations or equilibrium amount of each reactant and product. Very soon you are going to see that when we know the equilibrium concentrations of each reactant and product, so with that we can calculate our equilibrium constant Kc, right? So to calculate Kc, right, first we need to calculate the amount at equilibrium for each reactant and product. Sometimes this degree of dissociation is given in terms of percentage. Sometimes it will be like percentage degree of dissociation, percentage degree of dissociation. So in your questions, when it is a percentage degree of dissociation, you need to understand that it is alpha into 100, right? So in your question, if a percentage degree of dissociation is given, right? So from that, if you want alpha, divide with 100. Divide the percentage degree of dissociation by 100 to obtain alpha. And then you multiply alpha with initial amount, you will get the reacted amount till equilibrium, right? And once again, I am telling, this part is the most important part in chemical equilibrium, right? Like whenever you will be doing any numerical question in this chemical equilibrium chapter, now you do calculation of anything like Kc, Kp or whatever, you do any calculation. But if it is a numerical question from chemical equilibrium, every time you have to do this thing. In every question you have to do this thing. Equation, initial amounts, and what are the amounts at equilibrium. Equation, initial amount, and what are the amounts at equilibrium. This thing is the backbone, right? Because this thing can be calculated by knowing stoichiometry. And this thing you need in each and every numerical question of chemical equilibrium. And not only that, even this thing requires for your ionic equilibrium chapter, right? So finding concentration at equilibrium, finding amount of reactant product at equilibrium, you should be very good in that point. We should be very good in that point, right? Now, after understanding how we can obtain amount of reactant product at equilibrium, now let's see the first thing, that is Kc, and Kc can be also called as equilibrium constant in terms of concentration. And from this you get lots of question in your examination, you know that very well. So first let's understand what is the meaning of Kc. What do we mean by Kc? What is Kc? And along with that we will also talk that how this Kc can be calculated, right? We have two methods by which we can calculate Kc in this chapter, correct? So now in order to understand Kc, first you need to talk about a topic from chemical kinetics chapter, class 12th, right? In chemical kinetics chapter, you talk about rate of reactions, rate of reaction, right? How much fast, how much slow your reaction is, right? That can be decided by knowing the rate of reaction. Now, we have a law which is called as law of mass action, law of mass action, in which we say that rate of reaction is proportional to the active mass of the reactant. And active mass, just for your understanding, you can say that it is concentration. In your questions, in your numerical questions, you can understand that active mass is nothing but for you it is concentration. So law of mass action says that rate of a reaction is proportional to the active mass, or for your understanding you can say concentration. And when I say concentration in this chapter, you need to understand I am talking about molarity, because we have different concentration terms, molarity, molality, mole fraction, right, ppm. But in this chapter, whenever I say concentration, whenever I mention concentration, you need to understand I am talking about molarity, right? So rate of a reaction is proportional to the active mass or concentration of reactant, right? Now, if I take a sample reaction, let's say that I have this reaction. I have a reactant, right? Its coefficient is x. The coefficient of reactant is x, and I have product whose coefficient is, let's say, y. Now, for this reaction, when your reactant is converting into product, if you apply law of mass action, so that will tell you that rate is equals to rate constant, right, in forward direction, because it's a reversible reaction. So we have to talk about in both forward and backward. So here when I talking about conversion of reactant to product, so I am saying that I am having forward reaction, right? So rate is equals to rate constant into concentration of the reactant or active mass of the reactant to the power stoichiometric coefficient. You have to take stoichiometric coefficient as power, right? And in your chemical kinetics chapter, you will notice that along with law of mass action, you have a topic called rate law. In rate law, what will happen? You will have the same thing, rate equals to rate constant, concentration or active mass of reactant. But in rate law, the power here, it is not always equals to a stoichiometric coefficient. But in law of mass action, we write that stoichiometric coefficient is equals to the power of concentration term, right? And this relation can tell you definitely that rate is nothing but proportional to the concentration or active mass of reactant, directly proportional. So that means what? More the amount of reactant you have, more is your rate in forward direction, right? And if you talk about backward, so let me write it again for a reversible reaction. Let me write it again for a reversible reaction. Let's say that I have this reaction, A plus B gives C plus D, right? And here the coefficients are X, Y, P and Q. A, B, C, D are your reactant products, and X, Y and PQ are your stoichiometric coefficients for reactant product respectively. Now, in this case, because it's a reversible reaction, so I am saying that when AB is reacting to give CD, so that is my forward reaction. And when CD is reacting to give AB, so that is my backward reaction, right? Now here, if I talk about the rate in both the directions, forward and backward, right? So for forward, I can say that rate of forward will be equals to, okay, I wrote RB, I should write RF. Yeah, rate of forward equals to rate constant in forward into concentration of A and B to the power their stoichiometric coefficients, which are X and Y, correct? And in the same way, if I talk about backward reaction here, right? So for backward reaction, I can say ki rate in backward is equals to rate constant in backward, and when you do backward reaction like this, so there these products will act as your reactant, right? So for backward, I will be taking concentration of C and D, molarity of C and D to the power their coefficients, which are P and Q. So this is the expression we are getting by applying law of mass action in a reversible reaction. Now, if you recall the meaning of dynamic equilibrium, if you recall the meaning of dynamic equilibrium. So in dynamic equilibrium, I said that when equilibrium will be established, so at that state, rate of forward will be equals to rate of backward. Rate of forward will be equals to rate of backward. Now, the forward and backward rate, if I write from this expression, I can say that forward rate is rate constant in forward into concentration of A power x, B power y, and equals to rate of backward. I can say that rate constant in backward direction into concentration of product C power coefficient P, D power coefficient Q. Now you rearrange. Take the rate constants in one side and take the concentrations on other side. So if I take Kb in LHS and these concentrations of Ab in the RHS, I can rewrite and I can say that Kf upon Kb will be equals to concentration of C power P, D power Q upon concentration of A power X, concentration of B power Y. Right? Now, please understand here carefully. Students, this value, right? The ratio of forward rate constant upon backward rate constant is defined as equilibrium constant, right? This Kf by Kb is nothing but your Kc. This term only we define as Kc, equilibrium constant. So point is, if I know Kf Kb, if I know the forward rate constant and backward rate constant, so by dividing those two, I can get my Kc. This is one calculation of Kc. This is the way by which you can calculate Kc, by knowing the rate constant in forward and backward direction. Another point is, because this Kf by Kb is equals to the ratio of concentration of product and reactant, so if I know the concentrations at equilibrium, for all the products and reactants. So by knowing the molarities of product and reactant at equilibrium, from that also I can estimate the value of Kc. So Kc can be calculated by two ways, either Kf by Kb or concentration of products upon concentration of reactants raised to the power stoichiometric coefficient. Product upon reactant raised to the power stoichiometric coefficient at equilibrium. So that thing also gives you Kc. I hope that you have understood Kc. And also one thing, here you can notice that to get Kc, right, from concentration, we need concentration or molarity of all reactants products at equilibrium. And this is what I taught you just before this, that how you can calculate molarity or amount at equilibrium, right? Sometimes you can calculate that by knowing the degree of dissociation, and sometimes some extra informations will be given to you, right? Like they can directly say that this much amount of reactant is reacting or this much amount of product is getting formed. So from that also you can find out the equilibrium concentration, right, in a chemical reaction. Now, after Kc, we have another equilibrium constant, but it is in terms of pressure. Kp, right? The thing is, Kp is calculated just like Kc. The only thing is, when you calculate Kp, instead of molarity, instead of concentration, you will have to use pressure. Right? So let me take an example here, right? Let's say that I have this reactant converting to product. The coefficient of reactant R is X and the coefficient of product P is Y. Correct? Now, for this reaction, if I want to get Kp, I will have to talk about in terms of pressure. And one more thing, pressure is valid, right, only when these reactants and products are in gaseous phase. Right? So now suppose that initially when I started this reaction, the pressure of R was P. The pressure of reactant was P and initial pressure of product was 0. So this calculation is quite similar to mole. The way you calculate a number of mole or molarity at equilibrium, in the same way you can calculate pressures at equilibrium. Same way. So initially suppose that the pressure of R is P and pressure of P is 0, right? So at equilibrium, what will happen? The pressure of R will decrease and pressure of P will increase. Why? Because with time from initial state, the amount of R will decrease, the amount of P will increase. So when amount of R will decrease, so pressure of R will also decrease. And when amount of P will increase, so pressure of P will also increase. So now here let's assume that with time, right, till equilibrium, X amount of pressure of R is decreasing. X amount of pressure of R is decreasing, right? So it will become P minus X. Initially it was P, X amount is decreasing in the pressure. So at equilibrium it will become P minus X. And now you can notice that X part of this can produce Y part of this. So X part is decreasing, so its Y part will increase according to stoichiometry. So now it will become Y. The pressure of P will become Y here, right? So I am saying one thing, that the way you calculate number of mole at equilibrium or molarity at equilibrium, in the same way you can calculate pressure at equilibrium by using the initial pressure values. And here also you can use the degree of dissociation in the same way, right? If initial pressure is P, degree of dissociation is alpha, so till equilibrium P into alpha part will decrease. So at equilibrium the reactant will become P minus P alpha, right? Now if I have to calculate Kp for this reaction, how I will do that? Kp can be calculated as pressure of product P, pressure of P, power its stoichiometric coefficient Y, divided by pressure of reactant R to the power stoichiometric coefficient X. So same thing is there, right? In Kc, you take a concentration of product upon reactant raised to the power stoichiometric coefficient. So in Kp, you take pressure of product upon pressure of reactant at equilibrium to the power stoichiometric coefficient. One more thing, you all know very well that for gases, for ideal gases, we have this equation PV equals to nRT. And from here, you can find pressure as molarity into RT. Molarity into RT. So if you substitute these pressure values in terms of molarity into RT, you can find your relation between Kp, Kc. You can find your relation between Kp, Kc, right? Just by substituting. Like pressure of P can be written as molarity of P into RT, right? Pressure of R can be written as molarity of R into RT. So just by substituting that, you can find a relation between Kp and Kc. Let me do that for you. Let me establish a relation between Kp, Kc by using the same reaction which I used on the earlier previous slide, right? I hope you remember that I wrote Kp as pressure of product power Y upon pressure of reactant power X. Now my point is, I can substitute these pressures in terms of molarity like this. Molarity of P product into RT power Y upon pressure of R can be written as molarity of reactant into RT power X. Now if you distribute the power, you can rewrite it as molarity of P power Y into RT power Y divided by molarity of R power X into RT power X. Now if you notice carefully, this term is nothing but your Kc. Molarity of product upon molarity of reactant at equilibrium power stoichiometric coefficient is nothing but your Kc, right? So from here I can say that Kp is equals to, this term can be written as Kc, and what is left? RT power Y upon RT power X. So that can be written as RT power Y minus X. Now if you notice, even in your thermodynamics, when you calculate gaseous moles of product minus gaseous moles of reactant, so that term is called as delta Ng. In thermodynamics also you use this term delta Ng in the relation between delta H and delta U, the relation between enthalpy and internal energy. So here also you require that delta Ng. Delta Ng is nothing but a number of gaseous moles in product, which is Y here in this case, minus number of gaseous moles in reactant side, which is X here. So this Y minus X can be written as delta Ng. So in that expression of Kp Kc, in that relation of Kp Kc, when I will have y minus x, so that can be written as in general delta Ng. And students, again, this is a very, very important relation for you. You will be getting direct questions in your examination from this. Kp equals Kc times RT power delta Ng. RT power delta Ng. So till now, we have seen what is equilibrium, how to get concentrations or pressure at equilibrium, what is Kc, right, what is Kp, and the relation between Kp, Kc. And from these parts, from these topics, you get so many questions in the examination, right? So we will do some questions, but before that, let me tell you a concept which is skipped most of the time, but you shouldn't. We have a term like homogeneous and heterogeneous equilibria. Homogeneous and heterogeneous equilibria. And you should understand what is the meaning of homogeneous and heterogeneous equilibria. Students, when you say homogeneous equilibria, so that means when your reactants products, they are present in the same phase. Like suppose if I have this N2 gas, H2 gas, NH3 gas. So all the reactant and products, they are in gaseous phase. Similarly, in a reaction, if all the reactant products, they are in liquid phase or aqueous phase, so that is also called as homogeneous equilibria. But when the phase of reactants and products, they are not same, we have difference in the phases of either reactant or product, so then the equilibrium is called as heterogeneous equilibria. Like for example, I took this example of calcium carbonate solid decomposing into calcium oxide solid plus CO2 gas. Now if you focus, in this decomposition of calcium carbonate, our reactant is solid, one of the product is solid, but one of the product is gas. So here we have two phases, solid and gas. So when you have different phases in your reaction, so that is called as heterogeneous equilibria. That is called as heterogeneous equilibria. Right? And one more point, before we jump into the questions, before we jump into the practice about Kp, Kc and their relations and their questions, you need to keep one thing in your mind always, because I feel it's a very much noteworthy point here we have for the numericals. The noteworthy point is, suppose when you are calculating Kc, using the concentrations at equilibrium for any reaction. Now, out of your reactant product, if any reactant is in pure solid form or it is in pure liquid form, you can directly put its molarity as 1, because pure solid, pure liquid, they have constant concentration. So we just remove them by putting its concentration as 1. So while calculating Kc, right, for pure solid and liquid, its concentration you can directly put it 1. Or you can simply remove that from the expression of Kc. Similarly, when you calculate Kp, when you calculate equilibrium constant in terms of pressure, so for that case, whether it is solid, whether it is pure liquid, or whether it is an aqueous solution, in all these three cases, you can put your pressure as unity, 1 atm, 1 bar, right? 1 atm or 1 bar. So during the calculation of Kp, remember that for solid, liquid, aqueous, the pressure you need to put 1. And during the calculation of Kc, you need to put concentration unity for pure solid and pure liquid. Now students, let's practice some of the questions from that calculation of Kp, Kc and the relation between Kp and Kc. So what you can do here, like you can pause this question, right? You can do it by your own first, then later on you can match your answer, right? So the question is, for the reaction A to B, like your reactant is A and it is converting into product, that is 2B. The backward reactions rate constant, we know that the backward reactions rate constant is nothing but we represent it by Kb, right? So rate constant in backward direction is higher than the forward reaction rate constant. So for forward reaction rate constant, we denote that by Kf. So here Kb is higher than Kf by a factor of 2500. So at the temperature of 1000 Kelvin. So Kp for the reaction at 1000 Kelvin will be, right? So point is, in this question, if you notice, they have given that the rate constant in backward is higher than the rate constant in forward by a factor of 2500. So basically we have the value of kb by kf, which is 2500. Now point is, we know very well that kc is nothing but kf by kb. kc by definition it is rate constant in forward direction to that of rate constant in backward direction. So from this expression, if I calculate kf by kb, so kf by kb will be 1 upon 2500. So this 1 upon 2500 is nothing but your value of kc. Now here do not calculate it further, just keep it as it is. So for me, kc or equilibrium constant in terms of concentration, I got 1 upon 2500. Now we have to calculate kp here, not the kc value. But we know that kp and kc, they are interrelated with each other, and kp can be calculated as kc times r into t to the power delta ng. Now for me, I have to calculate kp, and the value of kc I have, which is 1 upon 2500, 1 upon 2500, now into r. The value of r is given in the question itself. We have to take it 0.0831. So r I can put 0.0831 into temperature is the given in the question, and it is 1000 Kelvin. So into 1000. Power delta ng. You know very well that delta ng we can get from the equation, and in this equation, if you notice, in the product side we have 2 moles of gases, and in the reactant side we have 1 mole of gas, right? So delta ng here will be number of gaseous moles in the product minus number of gaseous moles in the reactant. So 2 minus 1, it will be 1. So delta ng for us, it is 1. Now you have to do just the calculation part. It will be, students, if you multiply, 2 zeros can be cancelled here, right? From 5, you can cancel it by 5 times, 5 5s are 25, and this can be cancelled 2 times. So finally it is 0.0831 into 2, which will be 2, 3 into 2, 6, 8 into 2, 16, 1. So 0.0831 into 2 will be 0.1662, and in the denominator we have 5. If you divide, it will come out 0.0, 5 3s are 15, 1 6, again 5 3s are 15, 1 2, 5 2s are, and 5 4s are. So finally it is coming nearly 0.03324. And if you check the options, so here in the fourth option, option D, we have 0.033. So definitely D will be the answer. And if you carefully observe, this question is based on 2 points. One, Kc is nothing but Kf by Kb, and second, the relationship between Kp and Kc. Correct? And of course here the answer should be D, and it is your answer. And students, this question came in NEET 2025 examination. So same type of questions even you can expect in your exam. Question from calculation of Kc, or Kc as Kf by Kb, or the relation between Kp and Kc. Now, if you look at the next question carefully, consider the following reaction in a sealed vessel at equilibrium. So, in a sealed vessel, we have a equilibrium in which concentration of N2 is given, concentration or molarity of O2 is given, and concentration of NO is also given, right? And these NO, N2, O2 are nothing but your reactants and products. If 0.1 mole per liter of NO is taken in a closed vessel, what will be degree of dissociation? So in this question, you have to calculate the degree of dissociation. Although most of the time using degree of dissociation, what we do, we calculate concentrations of each reactant product at equilibrium. But in this question, we have to do it in a reverse manner, right? In this question, for our reaction, let me write the reaction once again for you. Reaction is twice of NO, gas, converts to N2, gas, plus O2 gas. So for this reaction, they have mentioned concentration of each term at equilibrium. So using that data, using the concentration of each term at equilibrium, we can easily calculate its Kc value, right? We can easily find out its Kc. Kc will be concentration of products, that means if I just write down the expression, so it will be concentration of N2 power coefficient, which is 1, into concentration of O2 coefficient 1, so power 1, divided by concentration of NO power 1. So from here, if I get my Kc, so concentration of N2 is 3 into 10 to the power minus 3 power 1 into concentration of O2 is 4.2 into 10 power minus 3 divided by concentration of NO. Okay, we should take power 2 because its coefficient is 2. So concentration of NO power 2, right? So concentration of NO, they have given 2.8 into 10 power minus 3. If you do square, so it will be like 2.8 into 2.8 into 10 power minus 3 into 10 power minus 3. So many terms will be cancelled here if you notice carefully, right? This 10 power minus 3 will cancel this 10 power minus 3 will cancel this. And now if you check carefully, so let me rewrite this as it is. It will be 3 into 4.2 upon 2.8 into 2.8. You can calculate it further, like these are these you can cancel from first of all 14, right? If you cancel this, remove these two decimals, 14 3s are 42 and 14 2s are 28, right? 3 3s are 9 upon 2.8 into 2 is 5.6. Now keep it as it is. We got my Kc, right? My Kc is 9 upon 5.6. Now the question is, for this reaction, we are starting with 0.1 mole of NO. So this is the initial concentration now. Initially, NO is 0.1 mole per liter. That's the concentration. Now by default, because they have not mentioned, I will assume that initially N2 and O2 was 0. Now suppose its degree of dissociation is alpha. If its degree of dissociation is alpha, then how much amount will react till equilibrium? So that will be 0.1 into alpha. If alpha is the degree of dissociation, then the amount reacted till equilibrium will be 0.1 into alpha, that is 0.1 alpha. So at equilibrium now, if I calculate concentration of each term, NO will be 0.1 minus 0.1 alpha, 0.1 initial amount and reacted amount is 0.1 alpha, right? And concentration of N2O2 will be, again according to stoichiometry, 2 mole of NO can produce 1 mole of N2, 1 mole of O2. So 0.1 alpha part will produce 0.1 alpha upon 2 part of N2 and 0.1 alpha upon 2 part of O2. Now point is, again this is a concentration at equilibrium. So from this concentration again I can find my Kc, right? But this time your Kc will be in terms of alpha, that means degree of dissociation. So from here if you calculate Kc again, so that will be concentration of N2 power 1, which is 0.1 alpha upon 2 into concentration of O2 power 1, which is again 0.1 alpha upon 2 power 1 divided by concentration of NO power 2, which is 0.1 minus 0.1 alpha whole square. Now the simple thing you have to do is this Kc and this Kc both will be same, because very soon you are going to see that in a reaction at a fixed temperature Kc remains constant. Kc will not depend on concentration, mole, volume, pressure and rest of the factors. Kc depends only on temperature. So if your temperature is constant, whether you calculate Kc from this given concentration or whether you calculate Kc from in alpha terms, both the Kc should be equal, right? So if you equate these two, you will get your answer, right? If you equate these two, right? If you equate this as 9 upon 5.6, you will obtain your answer. I hope that you can do the further calculation easily, correct? And if you do the calculation, your final answer will be 0.717. And please remember, in the questions of chemical equilibrium, sometimes we need to solve quadratic equations, right? So I hope you know that in general quadratic equation, if it is ax square plus bx plus c, so its roots are minus b plus minus under root of b square minus 4ac upon 2a. So using that formula, sometimes you will have to calculate, right, quadratic equation to get your answers, right? So in this case, you will get your answer as 0.717 just by equating these two. Just solve this, alright, and you will get your alpha, which is 0.717. And this question we got in NEET 2024, right? Now, let's see further. Let's see another question, right? And this time we have a little bit of logical question. We have a logical question. Read the question. I think this time you can pause this and you can do it by your own. It's a very easy question for you. Now, question is, in which of the following equilibria the Kp Kc are not equal? So we know the relation between Kp Kc. Kp is equals to Kc multiplied by R into T to the power delta Ng. Now, point is, students, please observe carefully. In any equation, if your delta Ng is 0, means you have same number of gaseous moles in the reactant side and in the product side. So in that case, your delta Ng will be 0. If your delta Ng is 0, then RT power 0 will become 1. And in that case, your Kp will be equals to Kc. So those reactions in which delta Ng is 0, in those reactions Kp will be directly equals to Kc, magnitude wise, right? Of course, they will have difference in unit, because Kp will have a unit in terms of pressure and Kc will have a unit in terms of concentration, but their magnitude will be same. So in the first reaction, if you notice, reactant side we have 1 mole of gas, product side we have 1 here, 2 mole of gas. So in this case, delta Ng will be 2 minus 1, that is 1. In the second case, in the product side we have 2 moles of gas, in the reactant side 1 mole I2, 1 mole H2, 2 moles of gas. So in the second case, delta Ng is 0. In the third case, if you notice, 1 mole here, 1 mole here, 2 moles of gas in reactant, and 1 mole here, 1 mole here, 2 moles of gas in the product. So in this case also delta Ng is 0. In the last options, we have 2 moles of gas in the reactant and again 1 and 1, 2 moles of gas in the product. In the third case also, our delta Ng is 0. So now the point is, in option B, C, D, because delta Ng is 0, so in these three options, our Kp, Kc will be equal. But the first case where delta Ng is 1, in this case Kp and Kc will be unequal, and this is what they are asking. In which of the following equilibria Kp, Kc are not equal? So our answer should be A, right? That means in first case, Kp, Kc will not be equal. Yeah, it's A. And this question again came in NEET 2024 itself. So now let's see the next question, right? Can you do it by your own now? Because I guess it's a very simple question of relation between Kp, Kc. Kp for the following reaction is 3. So they have given Kp. They have given what? Kp. Okay, whenever you read question, so always read the question carefully first. Then only you take your pen and you start solving. Many students, they do this mistake, like they do very rapidly, they read the question very rapidly, and due to which, right, sometimes they read the questions incorrectly. Don't do that, because by doing that, you will lose marks in your examination. Even if you are knowing the concept, then also you will lose your marks. So first read the question carefully and then you start solving it. So Kp is 3 here, temperature is 1000 Kelvin. This is our reaction, CO2 plus C gives to CO, and always check that whether your equation is balanced or not. What will be the value of Kc for the reaction at same temperature? So it's a direct question again, right? We know that Kp is equals to Kc times of RT power delta Ng. Now in this case, I have to calculate Kc. So Kc will be Kp upon RT power delta Ng. Now just put the values. Kp is 3 here. So 3 upon R is given 0.083 we have to take. For R, whatever value they give in the question, you need to use that, right? So here we have to use R as 0.083 into temperature is again 1000 Kelvin and power delta Ng. So for this reaction, if you notice, in the product side gaseous moles are 2, in the reactant side gaseous moles are 1, because this is solid, we cannot take that. So 2 minus 1, it will be 1. So if you calculate it, it will be something 3 upon 0.083 into 1000 is 83, right? So 3 upon 83. Can we do it round off, a little bit of round off, right? If you do a little bit of round off, it will be like you multiply 100 here and then multiply with 10 power minus 2. Now 300 upon 83 will be cancelled 3 point something times. You can do the exact calculation, of course. 3 point something will be there into 10 power minus 2. And the only option we have here is 3 point something into 10 power minus 2 is C. So of course in this case your answer will be C, and that's your answer. But I hope that you people will do exact calculation, right? Like separately you can do this division 300 upon 83 and it will that will come out 3.6. So 3.6 into 10 power minus 2 will be your answer. That will be the value of Kc in this question. And again students, this question we got in NEET 2022 examination. So you can see we got question from calculation of Kp, then Kc, and then questions from relation between Kp and Kc. Now let's do another one. Can you do it again by your own? 3O2 converts to 2O3. Now for the above reaction at 298 Kelvin, Kc is given 3 into 10 power minus 59. If the concentration of O2 at equilibrium is 0.04, then the concentration of O3. Again, it's a direct question, right? You know, if I just write down the expression of equilibrium constant for this reaction, the expression of Kc will be concentration of product, which is O3, power coefficient, which is 2, divided by concentration of reactant O2 to the power coefficient, which is 3. Now in this case, Kc is given for us. Kc is 3 into 10 power minus 59 equals to concentration of O3 we have to calculate. So keep it as it is, O3 power 2 upon concentration of O2 they have given 0.04, and 0.04 I think you can rewrite it as 4 into 10 power minus 2. 4 into 10 power minus 2. So concentration of O2 is 4 into 10 power minus 2 whole power, it will be 3. Now from here, if I cross multiply, I will get concentration of O3 power 2 as 3 into 10 to the power minus 59 into, right, 4 into 4 into 4. So that will be 4 into 4, 16, and 16 into 4, 64. So that will be 64 into 10 power minus 2 into 3 is 10 power minus 6. Now, if you do the further calculation, O3 power 2 will be 3 into 64, keep it as it is, and 10 into minus 59 into minus 6 will be 10 to the power minus 65. So instead of doing 65, what you can do, you can write that 10 to the power minus 64, and here you can put a decimal, right? Now if you do square both sides, then the concentration of O3 will be nearly under root of 3 into 6.4, and under root of 10 to the power minus 34 will be 10 to the power minus 32. If you calculate square root of this 3 into 6.4, so this will be roughly 6 into 3 is 18, square root of 18 is round of course it's 6.4, but I am doing rough calculation. So 6 into 3, 18, 3 3s are 9, 4, it will be nearly 4 point something. It will be nearly 4 point something. And if you see the options, so only in one case we have 4.38, right, into 10 power minus 32. So in this case, even without doing this further calculation, I can judge that my answer will be A, and only in one option they have this value 10 to the power minus 32, first one. So of course in this case answer will be A, but again, if you people find out the exact square root, so that will come out exactly 4.4 or 4.38, right? So this question was directly based on calculation of Kc, directly based on your understanding that equilibrium constant is nothing but concentration of product upon reactant to the power stoichiometric coefficient at equilibrium, right? And this question, of course, its answer will be A. Of course, your answer will be A. And this question we got in again NEET 2022. NEET 2022. So now I think you people have got an idea that what kind of question we can get from this KP-KC calculation. Can you do this question, but a little bit of more careful? Please be a little bit of careful in this question. First read it carefully, right? Then you can do it by your own again. So I am pausing it because you can pause, you can read the question carefully. Okay, now let me start because I can't wait much. I love solving questions. You should also. Question is, a 20-liter container at 400 Kelvin temperature contains carbon dioxide at a pressure of 0.4 atm and excess of strontium oxide SRO. Neglect the volume of SRO, okay. The volume of the container is now decreased. Volume is decreased means compression. By moving the movable piston fitted in the container, the maximum volume of the container, when pressure of CO2 attain its maximum value. Now, see, for this reaction, strontium carbonate converts to strontium oxide and CO2 gas. For this reaction, it's a very easy question. The length of question is more, but if you solve it, is a very easy question. If I write down the Kp, just the expression of Kp. So what I will do, I will write pressure of CO2, power coefficient which is 1, and for these two solids, I told you to take pressure as 1. So these two terms will not appear in your Kp's expression. So in this case, Kp is directly equals to pressure of CO2. Now its Kp is given 1.6 atm. So point is, when equilibrium will be established between CO2 SRO and SrCO3, right? So their Kp has a fixed value 1.6 atm. So if I put Kp 1.6 atm, so that will be your pressure of CO2 in your container that you can achieve, right? So that will be the pressure of carbon dioxide 1.6 atm. Now question is, this is your maximum pressure that you can achieve. So for this pressure, just calculate the volume. And how to do that? Can we apply P1 V1 equals to P2 V2 here, because our temperature is constant for this reaction? It's isothermal condition, and you know very well from your thermodynamics chapter that under isothermal condition P1 V1 should be equals to P2 V2. We can apply this formula here. So initially the pressure is 0.4 and the volume is 20 liter, right? So when equilibrium will be established here, so because Kp is 1.6, so the pressure of CO2 will be 1.6, and now this corresponding volume we have to find. So V2 or final volume, if you calculate, it will be 0.4 into 20 divided by 1.6. I think this will be cancelled 4 times, and 20 by 4 is nothing but 5. So finally, right, the volume will become 5 liter, and the only option here 5 liter is D. So D will be your answer in this case. Of course it is. D is your answer. So this question was lengthy, but if you understand this, right, you can solve it in a very easy manner. The only point here is, which you need to focus is, Kp is directly equals to pressure of CO2 in this, and Kp is given. So after mixing SRO with CO2, when equilibrium is achieved, we directly got the pressure of CO2 as 1.6 atm, and at that pressure we can just calculate the volume of your container. And this question again we got in the NEET 2017 examination, and these types of questions again you can expect in your exam to come. So after solving questions on Kp, Kc and their relation, right, now you can practice more questions by your own on this Kp, Kc. That will be your task, right? And we have provided the DPPs. From that you can practice more questions on Kp, Kc calculation and their relation. So now let's move further and let's see the next part in this chemical equilibrium, that is properties of equilibrium constant. Students, when it comes to equilibrium constant, you should have a better understanding about the value, about the meaning of your equilibrium constant. First point is, or the first property of equilibrium constant is, it depends only on temperature. Although I have said that earlier in this session only, that equilibrium constant, whether it is Kc, Kp, right? So equilibrium constant depends only on temperature. So in a process, if your temperature is constant, then your equilibrium constant will remain constant, right? But if you change your temperature, then only your equilibrium constant will change. And we have a proper formula for that, right? By changing temperature, how much your equilibrium constant is changing, right? If you want to calculate that, you can use your Van 't Hoff equation, which says ln of K2 by K1 equals minus of delta H0 by R into 1 by T2 minus 1 by T1, right? In this, K2 is your equilibrium constant at T2 temperature and K1 is your equilibrium constant at T1 temperature. And you know very well that when we convert natural log into log base 10, so we multiply by 2.303. So in that case, log of K2 by K1 will be delta H0 by R, and R, along with R you will have to multiply with 2.303, and then it will be 1 by T2 minus 1 by T1. So not very often, but sometimes we do get question from this Van 't Hoff equation, right? So please note down this formula, because from this you can calculate, right, that by varying temperature how your equilibrium constant changes. But always remember one thing, that equilibrium constant depends only on temperature. So in a reaction, whether you change pressure, volume, concentration, right, you add catalyst, anything you do, by that your equilibrium constant will not change, correct? Now moving further, let's see few more properties or few more operations of our equilibrium constant, because sometimes we get direct questions from these things, right? Suppose students, if you have a equation for which the equilibrium constant is known and you are reversing that equation. You are reversing means now you are making the reactant as product and product as reactant. So when you reverse a reaction, a equation, so equilibrium constant becomes reciprocal. Equilibrium constant becomes reciprocal. Like for example, if I have this reaction A to B, and for this reaction the equilibrium constant is K, right? Now if I switch the reactant product without changing the stoichiometric coefficient, like suppose here you have 2, here you have 3, right? If you just switch the reactant product without changing the stoichiometric coefficient like this, now 3B is your reactant and 2A is your product. So when you reverse this reaction, the equilibrium constant for the new reaction becomes reciprocal of the previous one. So for this reaction, if equilibrium constant is K, then for this one it will be 1 upon K. From this operation you get direct question in the exam sometimes, right? Similarly we have few more points here. If you multiply an equation with certain digit, certain number, right? Like suppose I have this equation, A converts to B, and for this equation equilibrium constant is K. Now my point is, I am multiplying with a number n, right, in this equation, in the both reactant product side, for the full reaction, full equation. So if I multiply with n, the equation will become Na goes to Nb. Now for this new equation, Na goes Nb, the equilibrium constant will be K to the power n. So whatever number is there from which you are multiplying the equation, right, for the new equation you have to just power that into the previous equilibrium constant. If it is K, then the new equation's equilibrium constant will be K to the power n. If you multiply here by 2, it will become K square. If you multiply by 3, it will become K power 3. If you multiply by 1 by 4, it will become K power 1 by 4, right? So this is another point we have for the equilibrium constant. And finally, one more operation is there, that is when you add two equations, right? Suppose I have an equation like this, 2A converts to 3B, and for this equation the equilibrium constant is K1, right? I have another equation which is 3p converts to q, and for this equation equilibrium constant is k2. So this type of operation, like where we add two equations, you must have seen in your thermochemistry chapter, in your Hess's law, right? In thermochemistry we have something like when we add two equation, so for the final equation the delta H will be added, delta H1 plus delta H2, right? So we have a similar thing but not same, right? In case of enthalpy, you just add those two enthalpies to get the enthalpy of addition equation. But in this case, suppose if I add these two equations, so my resultant equation will be 2a plus 3p converts to 3b plus q, right? Now for this equation, the equilibrium constant will be multiplication of these two. That means k1 into k2. So when you add two equations, right, for the final equation, you have to multiply their individual equilibrium constants. So for this one, the equilibrium constant will be k1 into k2. And from these operations, sometimes you get direct question. So these are not numericals. These are just an understanding that what happens to the equilibrium constant when you modify your equation, whether you reverse it, whether you multiply with certain digit, whether you add it, right? Even if you talk about subtraction, so when you subtract one equation from another, so in that case equilibrium constant will be division, like k1 by k2, right? Now the value of Kc of a reaction tells whether it is a product or reactant dominant reaction. So this is another feature or property of equilibrium constant, you can say, that for any reaction, students, if you know what is the value of Kc, so from that value of Kc, you can predict that whether your reaction is almost on completion or whether your reaction is happening to a very little extent, right? So when your reaction is almost completing, so then we call it that it is a product driven reaction. And when your reaction is not at all happening or it is happening to a very little extent, then we say that it is a reactant driven reaction. And that you can judge or guess by looking at the value of Kc. Suppose for a reaction, if the value of Kc is very high, like it is something like 10 power 10, 10 power 20, 10 power 5, like that. So that means if the value of Kc is large, right? So your reaction will happen to a very high extent in the forward direction, right? So when your reaction will finish, in your container, you will have very, very high amount of product. The amount of reactant will be very, very less, right? So because here, due to high value of Kc, we know that we have high amount of product. So that we call product dominant or product driven reaction, right? But on the other side, if you find that Kc is very small, it is something like 10 power minus 3, 10 power minus 10, 10 power minus 5, right? If your value of Kc is very, very low, so in that case, your reaction is happening to a very little extent. So after completion of reaction, in these cases, when your Kc is too low, you will have mostly amount of reactant, the amount of product will be very low. Now because in this case after completion we have higher amount of reactant and very, very less amount of product, so we say that these are reactant dominant or reactant driven reaction, right? Sometimes we get direct question from the value of Kc. So in your mind you should know this, right? That you don't have to just calculate Kc. You will have to understand Kc, right? And what information you can extract from the value of Kc, right? Higher the value of Kc, that means more the reaction is completing towards product. Lower the value of Kc, that means less the reaction is happening towards your product, right? Very, very low value of Kc, reaction is not at all happening. You have only reactant in your container. So after these properties of equilibrium constant, right? Now let's see another term apart from Kp, Kc, which is called as reaction quotient. It is denoted by Qc in your chapter. See, students, reaction quotient is a term that we have created to identify that at any state, whether your reaction is going in forward direction or backward direction. But the way we calculate Qc is quite similar as Kc. The only difference is Kc is calculated especially at equilibrium state, but Qc can be calculated at any random state, Like, let me take an example. Suppose I take my favorite reaction, N2 plus 3H2 gives twice of NH3, right? Now, suppose I started this reaction initially at t equals to 0 second by taking 20 molar N2 and 20 molar H2, and this was 0 initially, right? After 10 seconds, I saw that this became 19 molar. So 1 molar of N2 is reacting. So with 1 molar, it will react 3 molar. So it will become 17 molar. And with 1 molar of N2, I will get 2 molar of NH3. So like this, I can write down at different instants. Suppose after 20 seconds, it became 18 molar. So it became 14 molar. And it became 4 molar, right? After some 100 seconds, it became 16 molar, right? So now 2 molar is reacting. So with 2, 6 molar will react. It will become 8 molar, and it will become 8 molar, right? So like this, your reaction will proceed. You saw that earlier, right? During the course of reaction, amount of reactant will decrease, amount of product will increase if you start from the 0 amount of product. Now, suppose initially if I calculate concentration of product upon reactant ratio. So this is your QC at initial state. Suppose here if I calculate a concentration of product to the power stoichiometric coefficient upon concentration of reactants to the power stoichiometric coefficient, right? So this is again your QC at 10 seconds. So at any time, at any instant, when you calculate concentration of product upon reactant raised to the power coefficient, so that is called as QC. You know very well that when you will be calculating QC at equilibrium, right? So in that case, QC, Kc will be same, because Kc is also concentration of product by reactant raised to the power coefficient, and QC is also concentration of product by reactant raised to the power coefficient. So if you calculate QC, Kc at equilibrium, both will be equal. So we can write down this. We can write down this, that when your QC and Kc are equal, right? So that indicates you have already equilibrium state. You are at equilibrium state, right? But suppose for any reaction at some random instant, right, you calculated QC and you observed that your QC is less than Kc. Means what? The state where you are calculating QC, right, you have less amount of product, right, as compared to the amount of product that we will have at equilibrium. That's why you are getting lesser amount of QC. So when you get less value of QC than Kc, so that suggests that from this point where you are calculating QC, your reaction will move in forward direction, right? And when you calculate QC and it becomes greater than Kc, that means your reaction is already after equilibrium, right? You have a more amount of product as compared to the product of amount at equilibrium. So if your QC is greater than Kc, in that case, from that instant where you calculated QC, your reaction will go in backward direction. So from this, sometimes we get question, right? They will give you a reaction equation, they will give you its Kc value, and they will say that at certain instant concentration of reactant products are this. Now you evaluate whether it is equilibrium, whether from this state your reaction will go in forward direction, or whether from this state your reaction will go in backward direction, right? So you have to just compare the value of QC, Kc, and again reaction quotient is also a very important topic for us. Now we have a very important formula, although this formula you also discuss in the thermodynamics chapter, right? It is there in thermodynamics chapter also, because we have to relate between Gibbs energy and equilibrium constant, right? You know Gibbs energy from your thermodynamics, it is denoted by G, capital G, and equilibrium constant, you know, it is Kc. Point is, Gibbs energy or change in Gibbs energy can be given as standard Gibbs energy change plus RT ln of QC. Now this is your reaction quotient. So this is a generalized formula. This is a generalized formula. But this formula, students, if you apply exactly at the equilibrium state. So you should know one thing from your thermodynamics, that when equilibrium is established, so now because no net change is happening, no net process is happening, so at equilibrium the delta G will be 0. And please never get confused, at equilibrium delta G will be 0, not the delta G naught value, right? Do not get confused. Standard Gibbs energy change, it's not mandatory that it will be 0. The delta G will be 0 at equilibrium. So at equilibrium, if I apply this formula, I can say 0 will be equals to delta G naught plus RT natural log of, and at equilibrium this Q can be written as Kc. You saw just now, right? And if you rearrange, you will get a formula delta G naught equals to minus RT ln of K, or you can write it as minus 2.303 R into T log base 10 K, equilibrium constant. From this formula also you get questions in your examination. But point is, if you get question from this formula, you can consider that as a question of thermodynamics as well as chemical equilibrium, because this is from equilibrium constant, and this is from thermodynamics, delta G naught, standard Gibbs energy change. So please note down, because you will be getting direct question from this formula in your examination. So now students, let's see some of the questions that we get in our examination from the properties of equilibrium constant and the relation between Gibbs energy and of course equilibrium constant. So if you read this question carefully, right, here what they are saying, that at a given temperature and pressure, the equilibrium constant values for equilibrium given below are K1, K2. So we have two equations. One is 3A2 plus B2 gives twice of A3B, and another equation we have where A3B is converting into 3 by 2 A2 plus 1 by 2 B2, and for this equilibrium constant is K2. And what we have to do, we have to find a relation between K1 and K2. Now if you observe the equations carefully, you can see that in first equation you have A3B in the product side. In the second equation, you have A3B in the reactant side. One more difference is there. In first equation, the coefficient of A3B is 2, and in the second equation, the coefficient of A3B is 1. So what we can do here, if I reverse this equation, just think like this. If I reverse this equation, right? So when I reverse, it will become something like twice of A3B converting into 3A2 plus B2, right? And then if I divide or if I multiply the equation with 1 by 2, because if I multiply with 1 by 2, this will become 1 and I will get my desired equation, the second equation. So after reversing here, again if I multiply with 1 by 2, what I will get, in the reactant side 2 into 1 by 2 is now A3B, and in the product side 3 into 1 by 2 is 3 by 2 A2 plus 1 into 1 by 2 is 1 by 2 B2. So point is very simple here. In the first equation, if you reverse it and then you multiply with 1 by 2, you will get your second equation. Now point is, for the first equation, if equilibrium constant is K1, so when I will reverse it, right? So for the new equation, the equilibrium constant will be 1 by K1. I told you, right, that when you reverse, equilibrium constant becomes reciprocal. And finally, in this equation where you multiply with 1 by 2, so that will go into the power, right? So for now this equation in terms of K1, the equilibrium constant will be 1 by K1 whole to the power 1 by 2. I hope you know that power 1 by 2 means nothing but square root, right? So for this equation in terms of K1, the equilibrium constant is 1 by K1 power 1 by 2, and in terms of K2 it is K2, right? So can I say that here K2 will be equals to 1 by K1 power 1 by 2, or simply 1 upon under root of K1. So K2 will be equals to 1 upon under root of K1, and of course that's your answer here. K2 is equals to 1 by under root of K1. So here you have to just find a relation between equations, right? And this particular question, students, the relation between this K1, K2 we got in NEET 2024 examination. right? Now, let's move ahead. Let's see few more questions from the property part. Again, if you want, you can pause the video. You can do it by your own, and later on you can match your answers, right? So this time we have a question. I think it is related with reaction quotient this time. We have a reaction twice of A converts to B plus C. Now for this reaction, equilibrium constant Kc is given, which is 4 into 10 to the power minus 3. So Kc value is given for us. Now at a given time, the composition of the reaction mixture is, so at a given time, at some random time, not exactly at equilibrium, at some random instance, they are saying that the concentration of A, B, C, they are equal, and it is equals to 2 into 10 power minus 3 molar. So what we can do at this time, when the concentrations are 2 into 10 to the power minus 3, I can calculate the value of reaction quotient, right? QC in this case will be concentration of B power 1 into concentration of C power 1 divided by concentration of A power 2. Now, because all concentrations are equal, if you substitute that, concentration of B will be 2 into 10 power minus 3 power 1, concentration of C will be again 2 into 10 power minus 3 power 1, upon concentration of A square will be again 2 into 10 power minus 3 whole square. Now if you solve, it will come out simply 1. It will come out simply 1. So at that instant, when the concentrations are given, at that particular instant, for the equation for the reaction, the value of reaction quotient is 1, QC is 1. Now if you compare, your QC is 1 and the Kc for the reaction is 4 into 10 power minus 3, it is something like 0.004, right? So of course, Kc, which is 0.004, is much smaller as compared to this Kc. So in this case, at this instant, when the concentration of ABC are 2 into 10 power minus 3, I can say that clearly my QC is greater than Kc. And I told you that at any instant when you calculate QC, and if your QC is greater than Kc, that means from that particular instant, your reaction will go in backward direction. Your reaction will go in backward direction. So if you look at the options carefully, in the first case they are saying reaction is at equilibrium. No, reaction will be at equilibrium when your case QC is equals to Kc. Second, reaction has tendency to go in forward direction. Wrong, right? Reaction will have tendency to go in forward direction when your QC is smaller as compared to Kc. Now in the third case, reaction has tendency to go in backward direction. Yes. C will be the answer, right? Because my QC is greater than Kc, so I can clearly say that from that instant, from that particular moment, the reaction will have tendency to go in backward direction. So of course in this case, our answer should be C, and that is your answer. And again, this question, students, we got in the NEET 2024 examination, right? So now you can sense that what type of question you get from the properties of equilibrium constant and of course QC, reaction quotient, right? Deciding whether it is forward reaction, backward reaction, or your reaction is already at equilibrium. Now, let's see the next one. Again, we have a question from properties of equilibrium constant, right? Again, we have certain equations whose equilibrium constants are given, and for this equation, we have to find the equilibrium constant. See, this type of problem, right, where three equations are given, their equilibrium constants are known, and for one target equation, you have to find the equilibrium constant, right? Just try to get your target equation from the given equation. Just try to get this equation, whose Kc you have to find, from these equations. And you can do it on a target base, right? Like just look at your target equation. In this case, first you need NH3 in the reactant side with 2 coefficient. Now here, find out where is your NH3. NH3 is here. I want coefficient 2. I have coefficient 2, but I want in reactant side in my equation, but here they have given in the product side. So what I can do, I can just reverse the first equation. So students, if I reverse the first equation and if I rewrite that, the equation can be written as twice of NH3 gives N2 plus 3H2. Now point is, for this equilibrium constant was K1. Now if I am reversing it, so for this equation now, the equilibrium constant will be 1 upon K1. Now try to get the other terms. Now second term is O2. If you look at O2, so O2 is there in 2 equations. So if your component is there in your 2 equations, you can't decide. So skip that. Move on to the next parameter, next term. right? The next term you need is NO in your required equation. You require NO in the product side with a coefficient of 2. Now try to find where is your NO in the given equation. So here if you see, in the second equation you have NO in the product side with a coefficient of 2. Fantastic. I need NO in product side, it is in product side. I need with coefficient 2, it is with coefficient 2. So use that NO or use that second equation here and rewrite. It will be N2 plus O2 gives twice of NO, and for this equilibrium constant is K2. You know why I am rewriting it? Because at the end, when I will add these equations, I will get this equation. I will get NH3 in the reactant, I will get twice of NO in the product. Now, the third term you need is 3H2O. In the product side, you require water with a coefficient of 3. Now, if you see, in the third equation, you have water here, but you need water in the product side in your required equation. We have water in the product side only, but one point is there, one point of difference is there. I need coefficient of water 3, but in this equation, the coefficient of water is 1. So what I can do, I can multiply the whole equation with 3, right? And I can rewrite that. When I do that, the equation will become 3H2 plus 3 by 2 O2 gives 3H2O. But when you multiply with 3, the new equilibrium constant will be K3 power 3, right? Now, it's a very simple task. If you add these three students, you will get your desired equation because you have already written these, right, in order to get your target equation. You got NH3 from here, right? You got NO from here. You got H2O from here, right? So when you will add, right, you will get your desired equation and some of the terms will be cancelled automatically. You don't have to worry about that. Like N2 will be cancelled here, right? H2 will be cancelled here, right? And you are left with NH3O2 in the reactant and NO3H2 in the product, and that's what we need. But point is, when I add these three equations to get this equation, what operations I will have to do with equilibrium constant? I told you, when you add multiple equations, right, then equilibrium constants will be multiplied, right, to get the equilibrium constant of resultant equation. So when I add these three, I get this equation. So for this equation, now the equilibrium constant will be this into this into this, means 1 upon K1 into K2 into K3 power 3 into K3 power 3. Now if you check the options carefully, so K2 into K3 power 3 upon K1 is your first option, so A will be your answer. And exactly this type of problem you will be getting in your NEET examination from the properties of equilibrium constant, right? So I want you to be very good in this topic, especially this part, because it's a target based job. And one more thing, this type of problem you do in your thermochemistry in Hess's law, right? In thermochemistry you solve the question in the same way, where for different equations delta H are given, and for one equation you have to find delta H. In the same way, for certain equations equilibrium constants are given, and for this equation we have to find the equilibrium constant, right? So in this case, of course, your answer will be A, of course it is. And again this question from the relation between equilibrium constant we got in the NEET 2017 examination, right? Let's not stop here. Let's not stop here. Let's see one more question, and please read it carefully. It's a very interesting question for us. Question is, the value of equilibrium constant for a particular reaction is 1.6 into 10 to the power minus 12. Now you can imagine that when it is 10 to the power minus 12, so it's a very small value, right? 10 to the power minus 12 is like 0.00000000, 11 times 0 then 16. Now I told you already that when your Kc is very small, so you can say that your reaction is not at all happening, or it is happening to a very low extent, So by looking at the value of this equilibrium constant 1.6 into 10 power minus 12, what I can say that when the system will attain equilibrium, it will include, right, only or mostly reactants. I can't even say mostly, because mostly will be said when it is something like 1, 10 power minus 1, 10 power minus 2, 10 power minus 3, 10 power minus 5, up to 10 power minus 5. It is much smaller, 10 power minus 12. I can say that in this case, your reaction is almost not at all happening. So at equilibrium, you don't have product, you have mainly reactants, right? So in this case, your answer should be A. Yes, it is A. It is A. Right? Now, this came in the NEET 2015 examination. NEET 2015 examination. Correct? But I hope you have understood one thing, that by looking at the value of Kc, you can predict that at equilibrium whether you have more product or more reactant. Right? Now, let's talk about the final thing in this chemical equilibrium chapter, which is not at all calculative, which is completely, you know that it's conceptual thing. You don't have to do any kind of calculation now. Calculation is only up to relation between equilibrium constant, reaction quotient, Kp, Kc and their relation. Right? So now we see that what are the factors which can affect the equilibrium state. Right? You know that equilibrium state can be affected by different parameters like concentration, pressure, temperature, inert gas addition and that. And yeah, these are the 4 parameters for us that we have to discuss. But point is, how those parameters will affect your equilibrium state, that can be decided for us in an easy way by using Lee-Chatelier principle. I hope you know that Lee-Chatelier's principle, right? I just for a fun call it like Newton's third law of chemistry. You know, in physics we have Newton's third law which says every action has equal and opposite reaction. So Lee-Chatelier's is like the Newton's third law of chemistry. What it says, that in any reaction when equilibrium is established, so at equilibrium whatever change you do, the reaction will oppose that change, or reaction will act in a way to oppose whatever change you are bringing. Right? So point is, if I define Lee-Chatelier principle, it can be written as a reaction will always oppose any change at equilibrium. Now, why a reaction always changes its, why always it opposes the external change at equilibrium? Because for any system, for any reaction, equilibrium is the most stable state. So, your system, your reactions, once it has achieved the stable state, right? So, after achieving stable state, if you do any alteration, the system will try to again bring back on the same state, on the same stable state. So, that's why whenever you do any change, like you increase the concentration of anything, your reaction will try to decrease the concentration of same thing. You increase the temperature, so your reaction will try to decrease the temperature. You increase the pressure, your reaction will try to decrease the pressure in order to maintain stability or in order to maintain the equilibrium state. Right? Now, using this Lee-Chatelier principle, right, we have to discuss certain parameters. Right? The first one is effect of concentration, right, at equilibrium state. So let me take an example here first. Suppose all of you, if I have a sample reaction like this, reactant is there and product is there, that's it. I have taken one reactant and one product, just to explain in a simple way. Suppose that this reaction, when it achieved equilibrium state, so at equilibrium state, the concentration of reactant was X molar and the concentration of product is Y molar, X, Y, and this is your equilibrium state. Now point is, if I increase the concentration of product, like suppose it is Y, so I did Y plus 1. And how I can do that? I can add extra P in the container where this reaction is happening. So if I increase the amount of product from Y to Y plus 1, what your reaction will do according to Lee-Chatelier? If I increase the amount of product, the reaction will try to decrease again, right? So reaction will try to do it from Y plus 1 to Y again. And how the amount of product will decrease? If reaction goes in backward direction. So I can say that if at equilibrium concentration of product, right, is increased, if I increase the concentration of product, right, so due to that your reaction will shift in backward direction. Your reaction will shift in backward direction. And you know the reason, right? Because when you increase the concentration of product, reaction will try to decrease the concentration of product. And how product will decrease? If product converts into reactant, right? In the same way, if concentration of reactant is increased. Now think like this. If I increase the concentration of reactant from say x to x plus 1, again reaction will try to go from x plus 1 to x. So for that, it should decrease the amount of R. And how R will decrease? When it will convert into product, when it will go into forward direction. So when you increase concentration of product, reaction goes in backward direction. But when you increase concentration of reactant, your reaction will go in forward direction. And let me tell you, from these points, you get direct question in your examination, right? In the same way, you can also think about decreasing the concentration of reactant product. Point is, if I decrease the concentration of product, if I decrease the concentration of product, so when I decrease the concentration of product, reaction will try to increase the concentration of product. And how product can be increased? When reaction goes in forward direction. And finally, if concentration of reactant is decreased, so if I decrease the concentration of reactant, like if I remove a certain amount of reactant from the reaction, so when I decrease amount of reactant, reaction will try to increase the amount of reactant, and for that it will have to go into backward direction, right? So these are the 4 points regarding your concentration, and from this you will be getting direct question in your examination, right? How changing the concentration of reactant product can make your reaction from equilibrium state to go in forward or backward direction. Now, after concentration, we have to discuss few more parameters. Like the second parameter is effect of temperature. Now see, in temperature you don't have 4 points. Like in concentration we had 4 points. Increase in concentration of product, increase in concentration of reactant, decrease in concentration of product, decrease in concentration of reactant. So like concentration, in temperature you don't have 4 cases, you have only 2 cases, right? First point is in any reaction, either you can increase the temperature, or you can decrease the temperature, Only 2 possibilities there. Either you increase the temperature or you can decrease the temperature. Now point is, in case of temperature, in order to decide that whether your reaction is going in forward direction or backward direction, first you should have a knowledge that whether your reaction is exothermic or endothermic. And when I say exothermic, endothermic, so by default I am talking about forward direction. When you say that a reaction is exothermic, so it is exothermic in forward direction. When you say that a reaction is endothermic, so that means it is endothermic in forward direction, right? By default. So you should have knowledge regarding that. Like suppose I have this reaction in which again reactant is converting into product. Now I am saying that this reaction, right, is exothermic. So it is exothermic in forward direction, right? And in this case, the enthalpy change of this reaction should be negative from thermodynamics. Now automatically, if a reaction is exothermic in forward direction, so it will be endothermic in your backward direction. And for endothermic, the delta H should be positive. Now after knowing that whether it is exothermic and endothermic, now you can check and now you can decide the effect of temperature change. Please focus again on the Lee-Chatelier principle. Point is, if I increase the temperature of the system where your reaction is happening, so according to Lee-Chatelier, reaction will try to decrease the temperature, right? And how it will decrease temperature? By absorbing energy. So it will shift towards endothermic. Endo. Here you can't say towards forward or backward. Here you will have to say towards endo and towards exo. And later on, according to reaction, you can decide forward, backward. Like in this example, when I increase temperature, it should go towards endothermic. And this reaction is endothermic in backward direction. So for this example, for this particular reaction, I can say that when I increase temperature, the reaction will go in backward direction, because in backward direction we have endothermic reaction. Similarly, in a system where your reaction is happening, if you decrease temperature, so when you decrease temperature, reaction will try to increase temperature. and to increase temperature it will generate heat. And how heat is generated? By exothermic reaction. So in this case it will go towards exothermic reaction. Like in this case, in forward direction we have exothermic. So for this particular example, if I decrease temperature, the reaction shift in the forward direction from the equilibrium state. So from now on, please remember these points for temperature at equilibrium. When temperature is increased, right, it will go towards endothermic, and when temperature is decreased, it will go towards exothermic, right? So after effect of concentration and temperature, we have the third most important, that is effect of pressure. From this also we get question in the examination. Now, just like temperature, students, in case of pressure also, you will have only two cases, right? In a reaction in a system, either you can increase the pressure of the system, right? Or you can decrease the pressure of the system. Either you can increase the pressure or you can decrease the pressure, right? And in this case, you don't need to use the Lee-Chatelier principle. In a simple way also you can do it, right? Point is, when you increase pressure, right, so at higher pressure, particles will try to combine. And if you talk about in terms of gaseous reaction, so you can say that the gaseous particles will combine, right? So reaction will shift towards that side where you have less number of gaseous moles, right? In a simple way you can say like this, if you are not using Lee-Chatelier principle, if I increase pressure, then reaction shift towards that side where less number of gaseous moles are present, right? And if you want to do this according to Lee-Chatelier, you can do that also. If I increase the pressure, students, so reaction will try to decrease the pressure. And how reaction will decrease the pressure? By decreasing the number of gaseous moles, because the number of gaseous moles is directly proportional to pressure, PV equals to nRT, right? And similarly, if I decrease the pressure of a reaction, if I decrease the pressure of a system, so in that case, reaction will try to increase the pressure. And how it will increase the pressure? By creating more and more gaseous moles. So in that case, when you decrease pressure, your reaction will shift towards that side where more number of gaseous moles are present. Gaseous moles are present. Now let me tell you this with an example. Like my favorite example is, again, you know, Haber's process, right? N2 gas plus 3H2 gas gives twice of NH3 gas. Now in this reaction, first of all, if you notice, what are the number of gaseous moles we have in the reactant product side? So in the reactant side, we have 1 mole of N2 and 3 mole of H2. So in the reactant side, total moles of gases are 4, right? And in the product side, we have only 2 moles of NH3 gas, right? Now in this reaction, in this particular reaction, if I increase pressure, so it should go towards that side where we have less number of gaseous mole, which is in the product side. So in this reaction, when I increase pressure, it will go in forward direction because here we have less moles of gases. And in the same reaction, if I decrease the pressure, then here we have more number of gaseous moles. So by decreasing pressure, it will go in the backward direction. So in case of pressure also, you cannot directly say that whether it will be forward, backward. You will have to see that on what side you have more gaseous moles and on what side you have less gaseous moles. One more very important point is there. Suppose that in a reaction, if both side, both reactant and product side, you have same number of gaseous moles. So in that case, pressure will have no effect. And one more point, I can write it here. Like if reactant product both have same number of gaseous moles, then automatically in those cases, the delta Ng of that reaction will be 0. So you can remember like this, that for any reaction, for any gaseous reaction, if your delta Ng is 0, so in that case, it will have no effect of pressure, no effect of changing pressure. at equilibrium, right? Sometimes they can ask this, right? So if delta Ng is 0, by increasing or decreasing pressure, there will be no effect on the equilibrium state, right? But when delta Ng is not 0, it's positive or negative, you can decide if I increase pressure, it will go towards that side where we have less number of gaseous moles, and if I decrease pressure, the reaction will move towards that side where we have more number of gaseous moles. Now with this, we have done the three most important factors, that is concentration, temperature and pressure. Most of the time you will be getting questions from these three: concentration, temperature and pressure, effect on the equilibrium state. But we have one more point, that is effect of inert gas addition. I hope you all know inert gas. Inert gas means the gas which will not react either with your reactant or product. More commonly you can say that you can use noble gases like helium, neon, argon, krypton, xenon, right? So point is, when I add inert gas in a system for a reaction at equilibrium, I can do that in two ways according to thermodynamics. According to thermodynamics, the gas can be added either under isochoric condition. Isochoric means, I hope you know that when your volume remains constant, right? So before addition of inert gas and after addition of inert gas, the volume remains constant. So that is called isochoric addition. And one more addition you can do, that is under isobaric condition. Under isobaric condition. This is very simple point. See, when you add inert gas at isochoric condition, so because the volume remains constant and you are adding inert gas, you are not adding any of the reactant or product. So volume is constant, the amount of reactant product is constant. So of course their concentration, molarity will be also constant. So neither for reactant nor for your product the concentrations are changing, right? By adding inert gas at constant volume. So that means there will be no effect, right? You are not doing anything. So under isochoric condition, if you add inert gas, so there will be no effect on the equilibrium state. But when you add inert gas under isobaric condition, so in isobaric your pressure will remain constant but not the volume. Please focus here. In isobaric, right, before and after addition of inert gas, the pressure will be same before and after. But of course here the volume will change. Point is, when you add inert gas, so definitely it will occupy space, right, in your container. So to maintain constant pressure, the volume of container should increase, right? And volume of container can be increased only when you have more number of gaseous moles. So point is, under isobaric condition, when you add inert gas, right, to maintain pressure and to increase volume, reaction creates more gaseous moles. So directly I can say that under isobaric condition, when I add inert gas, it will shift towards that side where more gaseous moles are present. Now if you notice, the effect of inert gas addition on isobaric condition is quite same as when we decrease the pressure, right? And not only that, here when I say increased pressure or decreased pressure, from the pressure relation I can also relate with volume. You can also decide by increasing or decreasing volume how your reaction will shift, right? But now I think you are clear with all the four parameters, right? Especially the inert gas, in which isochoric has no effect. In isochoric condition, when we add inert gas, there is no effect on equilibrium state. But in isobaric, to maintain pressure, volume should increase, and to increase volume, reaction shifts in that side where more gaseous moles are there, right? Now one more point, if you talk about catalyst, right? So catalyst has no effect on the equilibrium state. Please remember that. A catalyst, right, will never change your equilibrium state, and also a catalyst will not affect the value of equilibrium constant, right? A catalyst only increases or decreases the rate of reaction, whether it is forward or backward. So catalyst can affect the rate of reaction but not the equilibrium state and not the equilibrium constant, right? So now I think it's time to see some of the questions from this Lee-Chatelier principle and effect of different parameters on the equilibrium state, right? So Take your pen, paper and brain. I always say you should have your PPB, pen, paper and brain, and try to do these questions before me, all of you. If you do it before me, I will be much happier. I will be more happier than you. So question is, higher yield of NO in this reaction. Okay, NO is product here, right? So higher yield of NO will be there when this reaction goes in forward direction. So higher yield of NO or forward direction can be obtained. Delta H of this reaction is given plus 180.7. So delta H is always for forward, right? And plus means it's endothermic. So this reaction is endothermic in forward direction and exothermic in backward direction. Okay, so they have given certain conditions and we have to decide that in which condition the reaction will favor forward reaction. So first condition is high temperature. Of course, yes. I told you that when you increase temperature, reaction decreases the temperature and it should go towards endothermic, and in forward we have endothermic. So A will definitely help you to make the reaction forward, to make more and more NO. Second is low temperature. No, of course high temperature is the condition, so low temperature will exactly do reverse. It will go towards exothermic. It will favor the backward reaction. High concentration of N2. N2 is your reactant, and I told you that in a reaction, whenever you increase the concentration of reactant, right, so it will go in forward direction. So whether it is N2O2, by increasing the concentration of both N2O2, reaction will go in forward direction. So higher the concentration of O2 will also help, and higher the concentration of N2 will also help. So here A, C, D, right, these three conditions are suitable for forward reaction or to prepare more and more NO. So A, C, D, if you check, it is present in the option B. So of course in this case your answer should be B, and of course it is B. The answer is B, and I hope that most of you have got the right answer in this before me, right? And this question came again in the NEET 2025 examination. So this is a very recent question for you, and again you can expect the same type of questions to be in your examination, right? Now let's do few more. Can you do this one again by your own? Pause it, do it by your own. Later on, of course, I will tell you what's the answer. So here the question is, for the reaction in equilibrium, N2, H2, NH3, delta H is minus Q, means in forward it is exo. Delta H negative means exo. So in backward it will be endo. A reaction is favored in the forward direction by use of catalyst. I clearly said that catalyst has no effect on equilibrium, so no. Decreasing concentration of N2. They are asking for forward, right? So decreasing concentration of N2. If I decrease N2, right, so reaction will try to increase N2, and N2 will increase when it will go backwards. So this is not the right option. Low pressure, high temperature. Okay, low pressure if I do. So when you decrease pressure, reaction goes towards that side where you have more number of gaseous moles. So here you have 1 mole, 3 mole, total 4 mole. So total 4 moles of gas we have in the reactant, and in the product side we have 2 moles of gas. So clearly more moles of gases are there in the reactant. So if I decrease pressure, the reaction will shift in left, backward direction. So even this is not possible. Now the last option is, if I increase pressure, so reaction will go towards that side where we have more number of gaseous moles, right? No, not more, sorry. If I have high pressure, then reaction will go towards that side where we have less number of gaseous moles. A kind of compression happens. You can remember like this also, that when you increase pressure, compression will happen, particles will join. So reaction will shift towards that side where you have less number of gaseous moles. So this will help in forward. Low temperature. If you decrease temperature, reaction will try to increase temperature. It will go towards exothermic. Exothermic is forward here. So this will also help you to go in forward. And higher concentration of H2. H2 is your reactant. So if you increase the concentration of H2, of course it will favor the forward reaction. So in this case, of course, A, B, C is not possible. The correct answer should be D, and that's your answer. So I hope that you have noted down those points, like what are the effects of concentration, pressure, temperature and inert gas addition on the equilibrium state, right? And very easily, once you have understood, you can always remember this. Like this is a topic, the Lee-Chatelier principle part. You don't have to revise it. It's a one-time study topic. Once you understand this clearly, right, you don't have to study this for the second time, right? But please be logical a little bit. So this question came in the NEET 2024 examination. Now let's not stop here. Let's see few more questions. Can you answer this by your own? I hope so. Pause it. Do it by your own. And if you want, you can give answer of this question in the comment box. I will personally check your answers. Yes, I can. I see the comments always, right? So you can write the answer in the comment box and I will give you a like if it is correct. So question is, which one of the following conditions will favor maximum formation of product? So again, product means they are asking for the forward reaction, which will favor the forward reaction. And again, delta H is negative, means in forward direction it is exothermic, right? In backward it should be endothermic. Now, low temperature. If I take low temperature, so yes, low temperature, when you decrease temperature, so reaction will increase temperature, it should go towards exothermic, exothermic is forward. So when I decrease temperature, reaction goes towards exothermic, so this will help in the forward. And high pressure, see the gaseous moles, here we have 1 mole, here we have 1 mole, 2 mole, and in the product side we have 1 mole. So reactant side has 2 gaseous moles, product has 1 mole. So when I increase pressure, reaction goes towards that side where we have lesser number of gaseous moles, which is in the product side. So again, even this will help you to go in forward direction. So in this case, answer will be directly A, right? Answer will be directly A. Yes, it is. Because it's a very easy thing, right? When you decrease temperature, reaction goes towards exothermic. When you increase temperature, reaction goes towards endothermic. When you increase pressure, reaction goes that side where you have less number of gaseous moles. And when you decrease pressure, reaction goes that side where you have more number of gaseous moles, right? And again, this question we got in the NEET 2018 examinations. So I tried to include almost each and every PYQ in these one shots, right? So that you can understand overall what kind of questions you get in your NEET examination, right? So even if you watch this session carefully, you can complete the whole chapter. If you have not done this chapter earlier in detail, right? Or if you have a problem in understanding in any concept, then this video can help you to understand each and every concept, and then comfortably you can solve each and every question from this chapter, especially this chemical equilibrium. And of course, we provide one shots of each and every chapter on our PW NEET English channel, right? So there you can find the other chapters of chemistry or other subjects also. So now let's move ahead and let's see what we have done in this session till now. So overall you can say that to memorize it, right? In this chemical equilibrium chapter, what are the things? The things are, first you should understand what is the exact meaning of equilibrium, right? A state when there is no overall change. Or for dynamic equilibrium, you can say that when the rate of forward is equals to rate of backward, right? Then finally, you have to do calculation of Kc, Kp, and also we have a very important relation between Kp, Kc, which is Kp equals to Kc into RT power delta Ng, right? Then we have to learn how do we calculate reaction quotient, right? Reaction quotient at any time is nothing but concentration of product power stoichiometric coefficient upon concentration of reactant power stoichiometric coefficient, right? And using QC, by comparing it with Kc, you can find that whether your reaction is at equilibrium or it has tendency to go in forward direction or in backward direction, right? Then you should have knowledge regarding the relation of equilibrium constant, like how equilibrium constant changes when you reverse a reaction, multiply with a number, when you add two equations, right? And a very important relation between Gibbs energy, right, and your equilibrium constant. From this also you get questions in your examination. Even in thermodynamics, we have this formula. And finally, the effect of concentration, temperature, and pressure, and addition of inert gas, right, on the equilibrium state. So these many topics, if you do it completely, believe me, you can do each and every question of your chemical equilibrium. But again, last thing is, after watching, after completing this video, after learning each and every concept, although I have tried to include as many questions I can, right, from my side, but still we have limited time, right? So what you can do now, after understanding all the concepts, right, you can download that DPP from the video description, right, or from the PW app, right, and practice each and every question. Like whenever you are doing a DPP from one source, right, so in that DPP, whatever number of questions are there, you will have to do it each and every question. You can't skip a single question, right? If there are 50 questions in the DPP, you have to do all those 50 questions, right? Because those questions, they have different concepts. So you don't want to miss any of the concept in a chapter, because no one knows what questions will be asked in our examination, right? So we have to cover each and every topic, and we have to prepare very well to ourselves for the examination, right? So that's all from my side in this chemical equilibrium session, right? We will meet in the next one short video. Thank you so much. Over and out. Bye-bye.